The winding resistance test of a transformer is a critical diagnostic tool used to assess the integrity and condition of transformer windings. The test helps identify mechanical or electrical issues that may not be visible externally but can significantly affect transformer reliability and performance. In the world of electrical engineering, ensuring the integrity and efficiency of motors and transformers is paramount. One of the critical diagnostic tools used for this purpose is the winding resistance test. The winding resistance test measures the resistance of the windings in motors and transformers. It helps detect issues such as shorted turns, poor connections, and problems with the winding insulation. A precise measurement of winding resistance is crucial because even a small deviation can indicate potential faults that might lead to inefficiencies or complete failure of the equipment. Continuity verification ensures winding is continuous, not open. Detection of inter-turn shorts identifies localized faults between turns within a winding. Condition of conductors highlights degradation due to thermal aging, corrosion, or manufacturing defects. Loose burnt joints identifies high-resistance connections, e.g., solder joints, brazed contacts. Tap changer contact integrity evaluates contact resistance and connection integrity through the full range of tap positions. When to perform new commissioning baseline readings. Routine maintenance, annually or as per O&M plan. After faults, to diagnose winding damage post-fault, e.g., short circuits, overcurrents. Post-transport inspection, after shifting large power transformers. Working principle, the DC winding resistance test operates on Ohm's law V = IR. A stable, low DC current controlled is injected through the transformer winding. The voltage drop across the winding is measured. Key considerations: AC currents are not used due to inductive effects, voltage lags current. DC injection avoids inductive reactance, providing true resistive values. This test is often used in conjunction with other tests like turns ratio, insulation resistance, etc. Test current selection IEEE 57152, 2013 Clause 7.2.7.2d. Current guidelines, recommended test current 1% to 15% of the windings rated current. Do not exceed 15%, excessive heating can change the resistance value and potentially damage windings. Lower test currents 0.1% to 1% are suitable for high-resistance windings, LV, CT windings. Temperature correction, the resistance of conductor materials copper aluminum varies significantly with temperature. IEEE 57.152, resistance at reference temp, measured resistance, standard temperature usually 75 degrees Celsius for transformers, measured winding temperature, temperature coefficient copper, 234.5 degrees Celsius, aluminum 225 degrees Celsius, alloy 230 degrees Celsius. Why correct? Enables comparison across time and between phases. Factory and field test comparison requires normalization to a common temperature. Winding resistance test equipment, common equipment, CPC 100 Omicron, advanced multifunctional equipment. Winding ohm meter dV power, precision low resistance meter. TTR sets with resistance option measure, ISA, etc. Ensure test equipment is calibrated and certified. General procedure for resistance testing, safety first, ensure complete de-energization and isolation. Disconnect HV, LV, N, tertiary bushings. Disconnect neutral grounding floating neutral, but ground transformer tank for safety. Clean and dry all terminals. Step-by-step test with CPC 100 Omicron, power on the CPC 100. Select, transformer TR tap check for OLTC. Input test configuration settings. Connect, current injection lead 6A DC out, 1 winding terminal e.g., HVA phase. Current return lead AC DC IN opposite terminal e.g., neutral. Voltage sense leads plus or minus 10 VV DC IN across winding under test. Short the 10A input port to plus 6A output per CPC wiring guide. Initiate test by pressing IO button, read results, record all data. Perform demagnetization before disconnecting leads. Importance of demagnetization. Why is it necessary? DC current aligns magnetic domains in the core saturation. On re-energization, residual flux causes high inrush current. Inrush can be up to 20x rated current, stressing protection relays and windings. How it happens: during DC test, core becomes polarized. If not demagnetized, energizing the transformer can cause it to saturate early. Low inductance, high inrush, possible relay misoperation or winding damage. Demagnetization is performed by applying reversing DC pulses, gradually decreasing to zero. CPC 100 and other modern sets do this automatically post-test. Connection configurations per transformer type. Auto transformer with tertiary, measure resistances for HV to LV, LV to tertiary, HV to tertiary. Each winding must be tested phase-wise ABC, and on all relevant tap positions if OLTC is installed. Two winding transformers, measure resistance for HV-ABC, LV-ABC, if OLTC is present, test at max, mid, and min tap positions. Record and compare for contact irregularities. Evaluation of results, pass criteria, phase resistance deviation less than 2% for same winding. OLTC step variation, smooth variation, no jumps. Resistance should align with factory test reports corrected to 75 degrees Celsius. Sudden increase possible loose contact or carbonized joint. The transformer winding resistance test is not only a mandatory commissioning activity but a vital condition monitoring tool. When performed methodically, it provides insight into winding health, joint integrity, OLTC performance, long-term thermal mechanical degradation. By integrating proper test procedures, temperature corrections, and demagnetization, engineers can ensure transformer reliability and prolong asset life. Transformer winding resistance testing is recognized as a cornerstone diagnostic procedure in the realm of electrical power engineering. It serves to examine the integrity of internal winding coils within power transformers by verifying continuity and measuring the level of resistance. By comparing measured values against historical data or manufacturer information, one can detect subtle deviations that could compromise the transformer's capacity to carry load. Abnormally high resistance values may indicate loose connections at the winding joints, while lower than expected values can suggest shorted turns within the coil. Both conditions, if left unattended, can lead to localized heating and accelerated deterioration of insulation materials. Early identification of such anomalies allows for maintenance interventions to be planned with precision and minimal impact on system availability. This methodology plays a critical role in ensuring a stable and reliable supply of electrical energy across the network. Performing winding resistance tests requires injecting a stable direct current through the winding under test while monitoring the resulting voltage drop across the winding terminals. High-precision test instruments are employed to provide a controlled direct current source and to measure voltage with high resolution. The current level is selected to produce a voltage drop that lies within the optimal measurement range without causing undue heating of the winding. Adequate dwell time must be allowed for the current to stabilize after initial application so that the inductive component of the winding has decayed sufficiently. Once the voltage reading has settled, the test instrument calculates the resistance by applying the relationship between voltage and current. Accurate results depend on calibration of the measurement device and careful attention to the contact quality at the test connections. Consistency in procedure is essential to establish reliable data for trend analysis. Winding resistance varies as a function of conductor temperature due to changes in resistivity of the copper or aluminum material. Testing at different ambient conditions or after loading can yield inconsistent values unless corrections are applied. Reference temperature is typically set at 20 degrees Celsius to align with factory test data. Measuring the actual winding temperature using surface or embedded temperature sensors at the time of testing allows for precise adjustment of the raw measurement. Correction algorithms compensate for the thermal expansion and conductivity variation of the conductor. Failure to perform this correction can obscure true changes in winding condition and hinder meaningful comparison of results over time. Ensuring accurate temperature compensation enhances the diagnostic value of the test. Transformers with multiple voltage taps require a systematic approach to test each tap position in order to evaluate the performance of the tap changer mechanism and associated internal connections. Each tap position is tested individually by connecting the test leads to the appropriate terminals and repeating the resistance measurement protocol. Consistent resistance values across adjacent tap positions indicate good contact integrity within the tap changer. Significant variations between taps can signify wear or oxidation on contact surfaces within the tap changer or internal bus bars. Such defects, if allowed to progress, may lead to arcing or failure during load transfers. Detailed analysis of tap-specific resistance values supports targeted maintenance of the tap changer and helps avoid costly unplanned outages. The integrity of leads, bushings, and terminal clamp assemblies has a direct impact on the accuracy of resistance measurements. High-resistance connections at these external points can mask internal winding conditions or introduce noise into the measurement. Prior to testing, it is advisable to clean contact surfaces, remove oxidation, and apply proper torque values during assembly of clamps. Visual inspection of bushing, porcelain, and conductor terminations can reveal evidence of overheating or contamination that might affect conductivity. Where possible, using dedicated test leads of known resistance and verifying their performance before measurement ensures that all readings reflect the true condition of the winding. Eliminating external errors provides confidence in test results and subsequent maintenance decisions. Thermal equilibrium of the transformer is important to minimize transient effects during winding resistance testing. If the transformer has been recently energized or heavily loaded, it is advisable to allow sufficient time for the windings to cool and for the oil and metal temperatures to stabilize. Ambient temperature fluctuations during test execution can also introduce variability in resistance readings. Scheduling testing during periods of stable environmental conditions reduces the need for extensive compensation and improves repeatability. Moisture ingress due to high humidity levels can also affect contact resistance at external connections. Maintaining careful control over the testing environment ensures that each measurement reflects the internal health of the transformer rather than external influences. Comprehensive record-keeping of winding resistance values forms the foundation for effective trend-based maintenance programs. Documenting test results alongside precise details of test conditions such as date and time, winding temperature, ambient environment, and tap position provides vital context. Historical comparison of these records enables engineers to detect gradual deterioration or sudden shifts in resistance. Threshold-based alarms triggered by significant deviation from baseline values can prompt follow-up inspections or alternative diagnostic tests. Integration of resistance measurement data with other diagnostic indicators such as dissolved gas analysis or partial discharge measurements creates a holistic view of transformer health. Leveraging trend analysis supports predictive maintenance strategies and informed asset management decisions. Incorporating winding resistance measurement into a structured transformer maintenance schedule enhances reliability and service life of critical assets. Periodic resistance testing is most effective when combined with other diagnostic procedures including turns ratio analysis, excitation current assessment, and insulation integrity tests. Setting testing intervals based on transformer criticality, loading history, and operational records optimizes resources while managing risk. Risk-based planning can prioritize testing of high-importance units or transformers operating under abnormal stress patterns. By adopting a continuous improvement mindset, engineers can refine testing protocols, calibrate instruments, and update acceptance criteria based on field experience. Reliable execution of these testing protocols plays a key role in achieving uninterrupted power delivery and minimizing lifecycle costs.